Good day, viewers all over the world. I welcome you to my class today. My name is Dr. Chris Esekaibe. I'm the owner of this YouTube channel. I am a chief lecturer in one of the most prestigious polytechnics here in Nigeria. I hold a doctorate degree in mathematics, a master's degree in mathematics, and a bachelor degree in statistics. I am a member of the Nigerian Mathematical Society and have written quite a number of books in numerical analysis and applied statistics. I also have publications in renowned publishing houses, and I've also presented papers in renowned conferences within Nigeria and outside Nigeria. I'm a specialist in numerical analysis, data analysis and modeling, and also statistical analysis and research. If peradventure you are an AI firm, you deal with artificial intelligence, you have models, AI models that you train on mathematical algorithms, or you are a research institute, why not you can contact me to be part of what your team of mathematicians and statisticians are doing. I've been involved in training AI models. I've worked with two US-based companies in training AI models. I trained their models using mathematical algorithms, and they were very grateful for the assistance I rendered to their company, to their organization. If you want to contact me, my contacts are here on the board. My first contact is +234. If you are calling from outside Nigeria, you add the code +234 8033021903. This first contact is for call and on WhatsApp. The second contact is +234 7066 297535. This second contact is only for call, not for WhatsApp. And my email is displayed, chrisdavid2015@gmail.com. Please, if you have not subscribed to my YouTube channel, try and do that quickly. And as you do, God will bless you. Share my videos in your social media platform. And as you do, God will bless you. The essence of this YouTube channel is to share knowledge in key topics in mathematics and statistics, preferably numerical analysis and applied statistics. And for those of you who have subscribed to the channel, thank you very much for sharing knowledge across the globe, because that is the key for this particular, that is the key purpose for this particular channel, to share knowledge across the globe. I work in Nigeria and I live in Nigeria. I will be looking forward to hearing from you. God bless you. I hope you have been enjoying my videos in numerical analysis and in statistics. If you have any challenge or you want me to teach any topic and upload it, you can put it in the comment section. It will be attended to. God bless you. So it's time for us to go to the business of the day. Today we shall be looking at a very simple topic. I call it simple because the topic is simple indeed. Please permit me to clean this part of the board so that we can have space to go ahead with our teaching. Today I want us to look at a very unique topic in mathematics in general. You see it in linear algebra, you see it in numerical analysis, you see it in business mathematics. This topic cuts across so many parts of mathematics, even in sciences, in engineering, in architecture. In different parts we make use of matrices. So today we shall be looking at introduction to matrices. This is part 1 of this topic. We shall be looking at the definition, the types, and algebra of matrices. Now, what is a matrix? Of course, matrices is the plural of it, while the singular is matrix. Matrix written in this form. So A matrix can be defined as a rectangular array of numbers or objects. It can be numbers or objects that are arranged in rows and columns enclosed in a bracket. This particular object, numbers, whatever it is, they are arranged in rows and columns. An example of a matrix is your kitchen cabinet in your kitchen. If you know your kitchen cabinet has rows and columns, different parchments where you put your plates, you put your spoons, you put your cups, different parchments like this, something like this, and you have it like this. At each parchment there is something arranged there. For instance, something like this. You can see it. You have the rows and you have the columns. You can arrange plates here, you can arrange cups here, spoons and different things. This is an example of a matrix. So it's a rectangular array. Array means arrangement of numbers. It could even be objects or anything, but they are arranged. Now, every matrix has a size or an order. When you talk about the size of a matrix, you can also call it the order of a matrix. If M is a matrix, and matrices are denoted in capital letters, so you should know that. So you cannot use a small letter like say small letter E to represent a matrix. No. So a matrix is written in this form: arrow times C. Arrow means the number of rows, while C means the number of columns. Arrow means number of rows, then C means the number of columns, means number of columns. That's what C is. Now, for instance, I can have, while M here is a matrix, arrow is the number of rows comes first, then by the number of columns. For instance, I can have A to be a 2 by 2 matrix. I can have it like this: small letter A, B, C, and D enclosed in the bracket. This is how matrix A is written. So this A, B, C, D are called the elements of matrix A. They are called the elements of matrix A. So the rows are lying flat on the down, while the columns are standing vertically. So it goes like that. So if I want to tell you the size of matrix A now, the size of matrix A is a 2 by 2 matrix. So why 2 by 2? Because it has 2 rows. The first one, of course, is the number of rows. Of course, the second one is the number of columns. So it has 2 rows: first row, second row, then first column, second column. So it is called a 2 by 2 matrix. So permit me to clean this part. So every matrix has a size. Every matrix has a size. Every matrix has a size. So, for instance, I can give another example. If I have matrix B equals 2, 4, 6, 5, 9, 1, for instance, of course, matrix B is a what? The size for matrix B will now be, let us count the number of rows: 1, 2, 3. So B is a 3 by, then how many columns? 1, 2. It's a 3 by 2 matrix. So it is important to know the order or the size of a given matrix. It is very, very important you know that. And also, some matrices are also called square matrices. For instance, if the number of rows of a matrix is equal to the number of columns, that matrix is called a square matrix. If the number of rows equals the number of columns, such a matrix is called a square matrix. For instance, I said if the number of rows equals number of columns, then the matrix is a square matrix. For instance, if I have D, remember matrices are denoted with capital letters. D equal 2, 5, 9, 1. This is a square matrix. It has 2 rows and 2 columns. If I say E is equal to 5, 9, 4, 3, 2, 1, 4, 2, 5. Of course, E is also a square matrix. E is a 3 by 3 matrix because it has 3 rows, 1, row 2, row 3. While D is a 2 by 2 matrix. So it is good you understand. So a square matrix can either be called an M by M matrix or an N by N matrix, depending on the one you wish to use. So it means that the number of rows and the number of columns are the same. That is how we represent a square matrix. It is important you know that. Now, permit me to go to some, I believe you are clear with the definition of what a matrix is. It's a rectangular array of numbers or objects in rows and in columns. And these are enclosed in a bracket. You can see it here, or a bracelet, whichever way or whichever name you want to call it. Now let us look at some special matrices that will help us. Permit me to clean the definition. I hope you have taken note of that. It is good we build a very solid foundation on this topic so that by the time we begin to go deeper, you will have a better understanding. So that by the time we begin to make mention of some notations, you will understand it better. Now I want to go into some special kinds of matrices. Some special kinds of matrices. We are going to be taking them one after the other. The first we are looking at is the diagonal matrix. The diagonal matrix. So the diagonal matrix is a square matrix. That means the number of rows and columns must be the same. This is a square matrix. A square matrix that has non-zero elements in the main diagonal. It's a square matrix that has non-zero element in its main diagonal. I will explain what we mean by main diagonal. Example, if I have matrix T equals P 0, 0, Q. You can see that the diagonal elements, the main diagonal, every square matrix has 2 diagonals. The main diagonal and the other diagonal. This is the main diagonal. You see it? The one that comes from the top left to the down right is the main diagonal. It's called main diagonal. is called the main diagonal. Then the one that comes from the top right to the down left is called the other diagonal. From the top right to the down left is called the other diagonal. So that is how it is. So a diagonal matrix is a square matrix with non-zero elements in its main diagonal. So you can see now P, Q are the main are the elements in the main diagonal. So T is a diagonal matrix. For instance, we can have another matrix R equals 5, 0, 0, 0, 2, 1, 0, 0, 4. Arrow is also a diagonal matrix. You can see here our T is a square matrix, it's a 2 by 2 matrix. The number of rows is 2, the number of columns is 2. So now look at it, now look at the main diagonal. Here, this and this, it has elements, they are non-zero. They are non-zero. Like we can change this one to 0. They are non-zero, so and other elements above or below it are 0. So arrow is a 3 by 3, it's a square matrix. It has 3 rows and 3 columns, like that. So you can see that's an example of a diagonal matrix. Now, number 2 kind of matrix is the unit or identity matrix. We have the unit or the identity matrix. Now, the unit matrix is also a diagonal matrix that has unity in all the main diagonal. It is a diagonal matrix. The unit matrix or the identity matrix is a diagonal matrix that has unity in all the elements in the main diagonal, and it is denoted by I. It is denoted by I, capital letter I. So it is a diagonal matrix with unity in its main diagonal. That means it has one. So we have, and it must be a square matrix. For instance, a 2 by 2 unit matrix is written as 1, 0, 0, 1. This is a 2 by 2 unit matrix. We can also have a 3 by 3 unit matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1, and so on and so forth. We can have also a 4 by 4 unit matrix, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So you can see the element in the main diagonal. I told you a unit matrix must first of all be a square matrix, and it is also a diagonal matrix. The difference between the unit matrix with the diagonal matrix is that the unit matrix has unity, that is 1. The element 1 in all its main diagonal. You will see it 1, 1. That's why it is denoted as I. That's why it's denoted as I, capital letter I. The identity matrix or the unit matrix. That's how it is called. It is a diagonal matrix. It is a square matrix. All diagonal matrices must be square matrix so that they can have the main diagonal and the other diagonal. You can see this one and look at the main diagonal element here, 1, 1, 1. Main diagonal element 1, 1, 1. The other diagonal, you can see 0, 0. The other diagonal, and so on and so forth. The other diagonal, you see it 0 like that. So you should understand that the unit matrix has unity in all its main diagonal. Now, permit me to progress as we go to another kind of matrix. We are looking at some special kinds of matrices. Permit me to clean this part. We have looked at the diagonal matrix. We have also looked at the unit or identity matrix. Now let us look at another one called the null matrix. Number 3, we are looking at the null matrix. The null matrix is also a special kind of matrix that has 0 in all its elements. It has 0 in all its elements. For instance, if I say B equals 0, 0, 0, 0, you can see it. B is a 2 by 2 0 matrix. All the elements in a null matrix are 0. And the matrix is denoted by letter 0. It is denoted by 0, letter 0. Okay, let me write it in letter 0. You can put it in this bracket. It's not O. O, letter O. It's denoted by letter O. That is what the null matrix is. So when you come across a matrix that has 0 in all its elements, that matrix is called a null matrix. Now, another kind of matrix which I'll be looking at, another special kind of matrix is triangular matrices. Triangular There are matrices that take the shape of a triangle. So triangular matrices, we have what we call the upper and lower triangular matrices. So we have the upper and lower triangular matrices. Now when we talk about triangular matrices, a triangular matrix is a square matrix. So it is a square matrix. It is a square matrix. A triangular matrix is square matrix in which all the elements below or above the main diagonal are 0. That is what a triangular matrix is. A triangular matrix is a special kind of matrix. It must be a square matrix, and when all the elements above the main diagonal are 0, it is called a lower triangular matrix. For instance, if I give matrix D equals P0 QR, you see it now? This is the main diagonal P, R, the main diagonal. If all the elements above it are 0, then it's an example of a lower triangular matrix. It will form a triangle at the lower part. It will form a triangle at the lower part. You see it? It will form a triangle at the lower part. So this is an example of a 2 by 2 lower triangular matrix. For it to be a triangular matrix, the first condition is that it must first of all be a square matrix. That means the number of rows must be equal to the number of columns. Then all the elements above the main diagonal must be 0. Let me give you an example of a 3 by 3 lower triangular matrix. If I have E equals 4, 0, 0, 2, 5, 0, 3, 2, 1. Look at this now. Look at the main diagonal, 4, 5, 1. All the elements above it, 0, 0, 0. So it's another example of a lower triangular matrix. It will form a triangle like this. You see it, a lower triangular matrix. So D and E are lower triangular matrices. You can even get for a 4 by 4, you can have 2, 0, 0, 0. You have 3, 4, 0, 0, 5, 2, 1, 0, 3, 2, 4, 5. You see it? It's an example of a 4 by 4 lower triangular matrix. You can see the main diagonal 2, 4, 1, 5 elements. Those are the elements in the main diagonal, and every other element above it, all other elements above it are 0, 0. So look at the main diagonal 2, 4, 1, 5 like that, and this is a 4 by 4 a lower triangular matrix. So when the elements that are above the main diagonal are all 0, you form a lower triangular matrix. When the elements above when the elements above the main diagonal are all 0, you get a lower triangular matrix. Now, let me give you an example of an upper triangular matrix. I will give you an example of an upper triangular matrix. For an upper triangular matrix, all the elements that are below the main diagonal are 0. For instance, if I have T equals 5, 2, 0, 3, you can see, look at the main diagonal here, 5, 3, and the element in the main diagonal, the element below the main diagonal is 0, so it's an example of an upper triangular matrix. It will form a triangle at, you can see it will form a triangle at the upper part. And another example, you can have x equal 5, 2, 1, 0, 3, 4, 0, 0, 2. You can see it. This is an example of course, a triangular matrix must first of all be a square matrix. You can see, look at the main diagonal elements, 5, 3, 2, and every other element below it are 0. So this is an example of an upper triangular matrix. So T and X are upper triangular matrices. When all the elements below the main diagonal are 0, you form what we call an upper triangular matrix. I hope that is clear. Now let's go to another special kind of matrix. Special kind of matrix. We are dealing with some special kinds of matrices. Some special kinds of matrices. Now we shall be looking at another special kind of matrix, transpose of a matrix. This is number 5 now. Transpose of a matrix. What does it mean to have the transpose of a matrix? The transpose of a matrix is simply a matrix with rows and columns interchanged. That means the rows and columns are interchanged. That is what we mean to have the transpose of a matrix. If, for instance, I have G is equal to P, Q, R, S, for instance, If I want to get the transpose of G, it is written as G raised to power capital letter T. That is how we write the transpose of a matrix. If G is a matrix, the transpose of G is written as G raised to capital letter T. So if we want to get the transpose of G, it simply means interchanging rows with columns. That is what it means. What is the first? Look at the first column here, P arrow, the second column QX. So we can interchange, we can turn this first column to become the first row. The first column is P arrow, so it will turn it to become the first row, P arrow. Then the second column is QX. We turn it to become the second row. It becomes QX, like that. That is what you are now going to have. So this first column becoming the first row, this second column becoming the second row. I can also take an example again. If I have Z equals 6, 5, 9, 2, 3, 1. Remember, look at it here now. G, matrix G is a 2 by 2 matrix. So when you interchange, you are going to have a 2 by 2 matrix. Now look at Z. For me to get Z transpose, it's written as Z raised to power capital letter T. What is the first column here? 6, 2. It becomes the first row. 6, 2. What is the second column here? 5, 3. It becomes the second row. 5, 3. What is the third column here? 9, 1. It becomes the third row. 9, 1. So you can see now, what is Z? Z is a 2 by 3 matrix. Z has 2 rows, row 1, row 2, that is Z. What is Z transpose? Z transpose is now, look at it now, how many rows? 1, 2, 3. So Z transpose has 3 rows, how many columns? 1, 2. 2 columns. So you can see that the number of rows has interchanged the number of columns. That is what it is. Z has 2 rows and 3 columns. Z transpose now has 3 rows and 2 columns. You can see it has interchanged. Now the same thing with G and G transpose. Look at it. G has a 2 by 2. There is 2 rows, 2 columns. Then G transpose has also 2 rows and 2 columns. So because it is a square, so when you get the transpose of a square matrix, the size remains. But when the matrix is not a square matrix, maybe a 3 by 4, a 4 by 3, of course the number of rows will interchange the number of columns. I believe you have seen some special kinds of matrices. Now permit me to go to algebra of matrices. Algebra of matrices. Algebra of matrices. Algebra. Now what do we mean by algebra of matrices? I hope you have subscribed to this channel. Please, if you have not subscribed, subscribe to this channel, share my videos in your social media platform. Be part of those sharing knowledge across the globe. The essence of this channel is to share knowledge in key areas in mathematics across the globe. And as you do, God will bless you. Today we are looking at a special kind of topic, introduction to matrices, that cuts across various fields in sciences, engineering, architecture, in different parts, even in social sciences. You come across matrices, using matrices to solve system of linear equations. If you don't understand the background of matrices, the fundamentals of matrices, it will be difficult to apply it in solving real life problems. So now we are looking at algebra of matrices. Algebra of matrices. When you talk about algebra of matrices, you are talking about addition, subtraction, multiplication, and of course determinant of matrices. So these are the subtopics under algebra of matrices. Now let us look at addition and subtraction of matrices. Now, if I have two matrices, A and B, can I add A to B, or can I add matrix B to matrix A? Now, the first thing you need to know is that before you can add two matrices together, the two matrices must be of the same size. They must be of the same order. That is the main condition for addition and subtraction of matrices. The two matrices must be of the same size and they must be of the same order. For instance, if I say A equals, if A is equal to 6, 2, 3, 9, and B equals 3, 2, 3, 2, 4, 3, for instance, they must be of the same size. Look at it here now. A is a 2 by 2 matrix. B is also a 2 by 2 matrix. So they are good to go. They have the same number of rows and the same number of columns. So they are compatible for addition and subtraction. But if, for instance, you have A to be a 2 by 3 matrix and B to be a 2 by 2 matrix, they are not compatible for addition and subtraction. You can see they both have the same number of rows, but they don't have the same number of columns. So they are not compatible for addition. So for two matrices to be added together, or for one to be subtracted from the other, the two matrices must be of the same order. They must be of equal size and of equal order. Now, if I come here to say matrix A plus matrix B, simply means, look at this, a simple thing. I'm matching each element. The first element here is 6. The first one here is 3 plus 3. Then I go again to the second one. This is 2 plus this one, 4. Then this one is 3 plus the matching element, 4. Then this one is 9 plus the matching element, 3. You can see, taking the elements in the same position and adding them together. You now come here, 6 plus 3 is 9, 2 plus 4 is 6, 3 plus 4 is 7, 9 plus 3 is 12. You will now result having also which is a 2 by 2 matrix. That is how it works. You see it? So in addition, there is what we call the law of commutative and the law of association. Of course, addition satisfies the law of commutative. So now, for us to check for subtraction, if I say A minus B will now be equal to, of course, you match them again, 6 minus 3, 2 minus 4, 3 minus 4, 9 minus 3. You match them like this. That is how it goes. So when you now write it now, when you now come here, at the end of the day, you will now see that the value that you have is different from that of addition. 6 minus 3 is 3. 2 minus 4 is minus 2. 3 minus 4 is minus 1. 9 minus 3, of course, is 6. So you can see Now, the question I will ask is is A minus B equals to B minus A? That is a question you can answer. Just like you saying, is 2 minus 1 equals 1 minus 2? The answer is no. 2 minus 1 is 1. 1 minus 2, of course, is not equal to 1 minus 2 is minus 1, so they are not the same. So for matrices, of course, you answer this question, is A plus B equal to B plus A? For instance, if I come here, if I say is 2 plus 2, or is 2 plus 4 equals to 4 plus 2? The answer is yes. So 2 plus 4 is 6, and 4 plus 2 is 6. They are good to go. So these are little things that you can prove with little examples. So for two matrices to be added, they must be of equal size. And for you to carry out subtraction, they must also be of equal size. That is the way it works. So you can see we have been able to carry out matrix addition and matrix subtraction. That is what we have been able to do. So now look at it: 6, 3, 6 plus 3, 2, 4, 2 plus 4, 3, 4, 3 plus 4, 9, 3, 9 plus 3. 6 plus 3 is 9, 2 plus 4 is 6, 3 plus 4 is 7, 9 plus 3 is 12. Then when you come to subtraction, this is 6 minus 3 is 3, 2 minus 4 is minus 2, 3 minus 4 is minus 1, 9 minus 3 is 6. So we have been able to carry out matrix addition and subtraction. Right now, we want to see how we can do with matrix multiplication. Matrix multiplication or multiplication of matrices. Multiplication of matrices. That's what we want to see now. We have two types of multiplication of matrices. The first one that we are looking at is what we call the scalar multiplication. We have the first one is the scalar multiplication. What does it mean to multiply a particular matrix by a scalar? A scalar is a quantity. For instance, if I have K into P, Q, R, S, this K here is a constant. A constant is a scalar. And I'm using this particular constant to multiply this particular matrix. It means I'm going to use that constant to multiply every element in that matrix. So we are going to have KP, KQ, KR, and KS. That is what we mean by scalar multiplication. For instance, if I have 4 multiplying a 2 by 3 matrix, 2, 5, 1, 3, 2, 1, 0, 5, 4. For instance, this 4 here is a scalar quantity. I'm multiplying this 3 by 3 matrix. Of course, it goes like this. You use 4 to multiply each of them. So you have 4 times 2 will be 8, 4 times 5 will be 20, 4 times 1 will be 4, 4 times 3 will be 12, 4 times 2 will be 8, 4 times 1 will be 4, 4 times 0 will be 0, 4 times 5 will be 20, 4 times 4 will be 16. So you can see how we have been able to use a scalar quantity to carry out matrix multiplication. So using another a scalar quantity to multiply a matrix, that is what we have been able to demonstrate. Now the second type is using a matrix to multiply a matrix. using a matrix to multiply a matrix. That one you can call it matrix multiplication. Now there is a standing law for you to carry out matrix multiplication. There is a standing law. The law states that the number of columns in the first matrix must be equal, underline this, must be equal to the number of rows in the second matrix. That is the condition. The number of columns in the first matrix must be equal to the number of rows in the second matrix. Permit me to clean this part so that we can see what we are doing clearly. The number of columns in the first matrix must be equal. Understand that. Must be equal to the number of rows in the second matrix. That is the condition for multiplying two matrices. Now I give you a first example. If I have matrix A, if A equals 2, 3, 4, 1, and B equals 4, 6, 1, 1. Now we are to get A dot B, that means A times B. Now let me do a simple analogy here so that you will understand before carrying out. You will know if the two matrices are compatible for multiplication or not. A is what? A 2 by 2 matrix. 2 rows and 2 columns. What about B? B is also a 2 by 2 matrix. Now what are we doing? We are multiplying a 2 by 2 matrix by another 2 by 2 matrix. And the law says that if the number of columns in the first matrix, this is matrix A now, this is matrix B. The number of columns here is 2. Then the number of rows here is 2. Look, the number of columns in A is 2. Look at it here. The number of columns in matrix A is 2. The number of rows in matrix B is 2. So they are good to go for multiplication. I come again. The number, look at the number of rows in matrix A, 2. Number of columns in matrix A, 2. Number of rows in matrix B, 2. Number of columns in matrix B, 2 now. And the law says if the number of columns in the first matrix, the number of columns in A here is 2. If it is equal to the number of rows in the second matrix, then they are good to go. Now what will they produce? Look at the resulting answer that you are going to have. The result will be, look at it, 2, 2. The final answer that you will get when you multiply a 2 by 2 matrix by a 2 by 2 matrix, you are going to produce another 2 by 2 matrix. Now let us go ahead and multiply this. So now this will go with this. So the first one you are going to have 2 times 4, 2 times 4 plus 3 times 1, 3 times 1. So you have done it this way. It goes like this. So that's why they must be the same. You can see it. 2 heads here, 2 rows here, 2 columns, 2 rows. So that's why the number of columns in the first matrix must be equal to the number of rows in the second matrix. Now the second one, it goes again. 2, you have 2 times 6, 2 times 6, then plus 3 times 1, 3 times 1, you cover it. Then you come to the second row here, 4 times 4, this will be 4 times 4, plus of course, this one will go with this one will come with this, plus 1 times 1, you have that. Then you come again to the second side, this will be 4 times 6, 4 times 6, plus, of course, the second one will come with this one, plus 1 times 1. I come again, let me give you the explanation. You come like this, you are taking this against this, that's why I did something like this. It's going like that. These 2 will be multiplied by 4, that's what you have here. These 3 will multiply by 1, you have done that one. Yes. Then the second one again, you go with this one again. These 2 will multiply this 6. These 3 will multiply this 1. That's what you have there. You are done with this first row there. You go to the second row again. This 4 will multiply this 4. That's what you have there. This 1 will multiply this 1. Then you come to the second one. Now this 4 will multiply this 6. This 1 will multiply this 1. So when you now come, 2 times 4, you are going to have 8. 3 times 1, 3 plus 3. 2 times 6, you are going to have 12. Plus 3 times 1, you are going to have 3. 4 times 4, you are going to have 16. Plus 1 times 1, you are going to have 1. 4 times 6, you are going to have 24. 1 times 1, you are going to have 1. That's what you are going to have. So coming here now, your A dot B, which is your A times B, 8 plus 3 will be 11. 12 plus 3 will be 15. 16 plus 1 will be 17. Then 24 plus 1 will be 25. So you can see it's also a 2 by 2 matrix, which is the result we are expecting. That is what you now have as your A times B. So you can see that this is interesting. It's getting interesting. Now I will take another multiplication so that you can get it clearly. I'll take another example on multiplication. Now, permit me to write. Can I clean this part so that we have space to write? Let me clean this part so that we can have space to write. I hope you have taken that so that we can have enough space to carry out our second example on matrix multiplication. So now we are going to take another example. Here, if A equals 1, 2, 5 and 3, 1, 2, comma, and Q, of course, a matrix should be denoted with capital letter. Q is minus 2, 1, 3, 1, 2, 4. Don't allow them to be too close. 2, 4. Now, look at it. Our A is a 2 by 3 matrix. It has 2 rows and 3 columns. So look at it now. You have a 2 by 3 matrix multiplying another. Our Q is a 3 by 2 matrix. It has 3 rows and 2 columns. So multiplying a 3 by 2. So now look at the number of columns here. In A is equal to the number of rows. They are 3 and they are 3. They are equal. So they are good. Now what are you going to produce when you multiply these two? Results will be equal to a 2 by 2 matrix. 2 by 2. So this is the condition for compatibility for the two matrices. So when we multiply A by Q, we are expecting the result to be a 2 by 2 matrix. Now let us go. So now it goes, our AQ will be equal to, it's going to be a long one. Now look at it now. It goes like this, as I said, it goes like this. So you are going to have this multiplying this. That's what we are going to have. We are going to have this multiplying that. So we are good to go now. So the first one, you are going to have 2 times, you are going to have 1 times minus 2 plus this 2 will now take on this 3 plus 2 times 3 plus this 5 will now take on this 2 plus 5 times 2. You see that? Then you come to the other side, this one will take on this one. You have 1 times 1 plus, of course, this 2 will take on this one, 2 times 1, then plus 5 times 4. I come again, 1 times minus 2 plus 2 times 3 plus 5 times 2. You have taken the first part. Then this again goes with the second one. This will be 1 times 1 plus 2 times 1 plus 5 times 4. You have that. Then now it's time to use the second row. This one will be 3 times minus 2 in brackets plus 1 times 3 plus 2 times 2. So you have taken this against this. Now we want to take this against this. So the next one will be 3 times 1, 3 times 1 plus 1 times 1, 1 times 1 plus 2 times 4 plus 2 times 4. So of course it's given in the bracket, you cover it. So our A dot Q will be equal to, you begin to write them out. 1 times minus 2 is minus 2. 2 times 3 is 6 plus 6. 5 times 2 is 10 plus 10. Then here 1 times 1 is 1 plus 2 times 1 is 2 plus 5 times 4 is 20. Then 3 times minus 2 is minus 6 plus 1 times 3 is 3 plus 2 times 2 is 4. 3 times 1 is 3. 1 times 1 is 1. 2 times 4 is 8. So our AQ will now be minus 2 plus 6 plus 10. That will give us 14. We are going to have 14. 1 plus 2 plus 20, you have 23. Minus 6 plus 3 plus 4, that will give you plus 1. 3 plus 1 plus 8, that will give you 12. So you can see it's a 2 by 2 matrix as already seen. It's a 2 by 2 matrix. So that will give you the multiplication of A by Q. You have 14, 23, 1, and 12. So please, it is important for you to note that our A square is A times A. Our A raised to power 3 is A times A times A, or you can call it A times A square. And also our A raised to power 4 is written as A square times A square. Don't do it like this. Don't write, if for instance you have A equals 6, 3, 4, 2. Don't write A square to be equal to, you now begin to square each of this. You now say 6 square 36 because it is demanding for A square, 3 square 9, 4 square 16, 2 square 4. this is wrong. Absolutely wrong. Simply a squared will be equal to a dot a, and that will be equal to 6, 3, 4, 2 multiplying 6, 3, 4, 2. That's what you are going to have. And you are going to produce something like this. You go 6, you have 6 times 6 plus 6 times 6 plus 3 times 4 plus 3 times 4. Then the next one will be 6 times 3, 6 times 3, 6 times 3 plus 3 times 2 plus 3 times 2. Then the next one will be 4 times 6, 4 times 6 plus 4 times 6 plus 2 times 4, 2 times 4. And the next one will be 4 times 3, 4 times 3 plus 2 times 2 plus 2 times 2. So you can see this is what you are going to have. So you are going to have that 6 times 6 is 36. 3 times 4 is 12. 36 plus 12, you are going to have 48. 6 times 3 is 18. 3 times 2 is 6. 18 plus 6, you are going to have 24. 4 times 6 is 24. 2 times 4 is 8. 24 plus 8, you are going to have 32. Then 4 times 3 is 12. 2 times 2 is 4. 12 plus 2. 12 plus 4, you are going to have 16. So this is what you are going to have as your a squared, not this one, squaring each of the elements. So please take note. It is as important as this. You do it this way. If it is a raised to the power 3, you multiply by another a, and so on and so forth. So the law of matrix multiplication must be followed. It must be followed. This now, let us take the last part of matrix algebra, which is the determinant of matrices. We'll just take the determinant of a 2 by 2 matrix, then we'll continue in part 2 of this introduction to matrices. I will introduce the determinant of a matrix, then I will now continue in part 2. We will now continue in part 2. So determinant of a matrix, and its uses. I will just take it and we introduce it. And so a determinant is a single value that represents a matrix. A determinant, it is a single value that represents a matrix. That is what a determinant is. So if A is a matrix, the determinant of A, of course, if A is a matrix, then the determinant of A is written as this, or you simply write determinant of A. Whether determinant of B, determinant of C, whichever matrix, you write it in this form, or you just simply write det A, D-E-T-A. That is what it means. Now, like as I said, we'll just consider the determinant of a 2 by 2 matrix. In the part 2 of this video, we'll be coming up with determinant of 3 by 3 matrix and how we can use determinant to solve problems. We'll be looking at more complex matrix algebra in the part 2 of this video. It will be very, very interesting. So let me introduce determinant and then we call it a day. For instance, if A is equal to A, B, C, D, A is a 2 by 2 matrix. Note you can only get the determinant of a square matrix. So you can only get the determinant of a square matrix. So the matrix must be a square matrix. The number of rows must be equal to the number of columns. Now this is how you calculate the determinant of A. For instance, you can write it as this, or just simply that A is simply, now, like I told you, if this is a 2 by 2 matrix, this are the elements in the main diagonal. A, D are the elements in the main diagonal, while B, C are the elements in the other diagonal. So you multiply the two elements in the main diagonal together. A times D will be AD. Then you subtract the multiplication of the other one. The other diagonal is BC. So B times C will now be BC. So this is now the determinant of matrix A. For instance, if I have matrix B equals 6, 5, 2, 1, the determinant of B will be equal to the element in the main diagonal as 6 and 1. So you are going to have 6 times 1 minus the other elements in the other diagonal will be what? 5 times 2. And that will now be equal to 6 times 1 is 6 minus 5 times 2 is 10. So it will now be minus 4. So you can now come and write it as the determinant of B is equal to minus 4. So determinants can either be positive, determinants can be negative. Now, we have two types of matrices that are defined based on the value of the determinant. So we have what we call the singular matrix, and we have the non-singular matrix. For the singular matrix, the determinant is 0. For the non-singular matrix, determinant is not 0. Like for instance, here now, our B is a non-singular matrix because the determinant of B is minus 4. If the determinant is positive or negative, that means there is a value for it, whether it is positive or negative notwithstanding. So B is a non-singular matrix. So matrix B is a non-singular matrix. Now, let me give you an example of a singular matrix. If I have matrix D equals 2, 5, 4, and 10. For instance, the determinant of D, of matrix D, will be equal to, look at it here, the main diagonal 2 and 10, you are going to have 2 times 10 minus then the other diagonal 5 times 4. So that will be 20 minus 20, that is equal to 0. So the determinant of D is 0. So D, matrix D, is a singular matrix because it has the determinant to be 0. So when you calculate the determinant of a matrix and you get 0, that matrix is called a singular matrix. And when you calculate the determinant of a matrix and it is non-zero, it can be positive or negative, then it is a non-singular matrix. Beloved, we are going to continue with this video in part 2 of Introduction to Matrices. We'll be coming up with the determinant of a 3 by 3 matrix, and we'll be coming up with the adjoint of a matrix, the inverse of a matrix, how we can use the matrix to solve a system of linear equation and other algebra of matrices. That's what we'll be looking at in part 2 of this video. So please, I want to appreciate you and thank you for watching this video to the end. If you have not subscribed to my channel, to my YouTube channel, Dr. Chris Isekaibe, please ensure you do so. Share my videos in your social media platforms. Share it with your friends, among your friends. Be part of those sharing knowledge across the globe, because the essence of this channel is to share knowledge in key topics in mathematics and statistics, preferably across the globe. So be part of those sharing knowledge across the globe. Thank you for subscribing. Thank you for sharing my videos, and God bless you. I'm speaking to you. If you are an AI firm, maybe you are in the US or any part of the world, you train AI models with mathematical algorithms. I am a mathematician. I'm also a statistician. I have a PhD in mathematics, and I specialize in numerical analysis. I have worked with 2 US firms, AI firms. I assisted them in training their AI models, and they were very grateful for that. If you want me to be part of those training your AI models, training them with mathematical algorithms, why not? You can contact me. My contact numbers are at the beginning of this video. You see my contact also in the description of my YouTube channel. You'll see my email address and my contact numbers there, my WhatsApp number. I'll be expecting your call. I'll be looking forward to hearing from you so that I can be part of what you are doing across the globe. Thank you again for watching this video patiently. God bless you richly. Enjoy the rest of the day. Bye.